So then let's move on. So far we have looked at this following way of compensating the amplifier. So what we did is the following: we tried to keep the open loop poles far apart like this, right? So this was one technique. What was the other approach we saw? We saw that instead of keeping the open loop poles far apart, we let them be close by, but you add an LHP0. This will again ensure that the closed loop poles do this and fall back on the real axis, so you are fine. Again, the example I give is this: poles are like naughty children, right? In a classroom, if there are two naughty kids, if they are placed close to each other, they will do all sorts of random things and class goes unstable. So in olden times, the teacher used to make sure that one guy sits here, other guy sits there, so that class is stable. That is essentially Miller compensation. You make sure the poles are split apart. Now this is basically the technique where the teacher lets the two kids stay nearby, but make sure an adult is sitting in between, so that they kind of behave properly. Right? So that's this technique. So till now we have focused only on this. So it's time that we look at the second thing. Okay. So this is what we'll focus. So let me first draw a two-stage OTA. So this is the first stage. So let's say this is GM1, G1 and C1. I'll draw the second stage, GM2, let's say G2, C2, and then I'll also add the load also. So I have a load conductance GL and a load capacitance CL. So it's your plain old two-stage OTA. I have not done anything new here. So here, as you know, if I look at the poles here, they might be close enough. It's not great. So now my goal is to try and ensure that I add an LHP0 here. Right? So tell me, how can I introduce a 0 in a circuit? Any suggestions? Capacitor in loop meaning? Okay, think of it this way. Intuitively, we know that we will have zeros in a circuit if the output is obtained as sum of two different voltages, or at the output I have two different currents but different phase shifts getting added. Right? So remember that in circuits it is much more easier to add currents, because if I have one branch carrying current I1, other carrying current I2, I just do this. KCL ensures that this current is I1 plus I2. Right? So here you see that the second stage, that is already processing the input Vin and pushes out a current in proportional to Vin, right? And this current has a phase shift because of this RC. Now if I can somehow add another current at the output that is proportional to the same input, but it does not contain any phase shift, then hopefully I would have added a current, I would have added a 0, because now I'll have one current without any phase shift, another current with phase shift. At some complex frequency they will add to 0. Is that right? So now tell me, what I have to do is the following. I have to sense this voltage and convert it to a current. What is one block that senses voltage and converts that voltage to a current? OTA, voltage controlled current source. So again we have to put another OTA. So let me mark it here. So I need to have another OTA here that senses the same input. Okay. And I need to make sure the current is added here. Right? So let me call this GM3. But before finalizing, I have to figure out the signs of A and B. Oops, sorry. Yeah. So how do you think we can figure out what should be plus and what should be minus? We should have phase shift, but what exactly you mean by phase shift? Huh? No, if the two currents are out of phase, see, do you want the 0 to be in left of plane or right of plane? Left of plane. So remember, here I have two currents. One current will have S times some V in. Other current will be just proportional to V in, some GM times V in, blah blah blah. These two should add with the same polarity to 0, only then S will become negative. Correct? Right? So which means here, what can you say about the current pushed by GM2? Do you think it is positive or negative? Negative, because it's inverted. So what can you say about this current then? So what should be minus here? AS minus. If you flip it around, you are gone. You will introduce an RSP0, you are actually worse. Cool. So this is one way in which you can do this, introduce LSP0, and this is one commonly used technique. Okay, and also the moment I add GM3, that will add its own conductance and capacitance. So let me also mark that. So maybe I'll use the same color. So this is the conductance and capacitance of the third stage. Okay. So let me actually copy this. I don't want to draw all resistors and capacitors, so I'll show only one of them and club everything. Okay. So I'll say that I have one GL prime and CL prime. So as usual, GL prime is G2 plus G3 plus the load conductance. CL prime is C2 plus C3 plus C. And this technique is called the feed-forward compensation for obvious reasons. Great. So you guys know how this kind of makes a system stable in frequency domain, because we already saw through the root locus blah blah blah. It is also worthwhile to understand how this is going to work in time domain. So let's do that now. And for that, I'll assume that I'm going to put this guy in negative feedback. I'll put it in unity feedback like this. Okay. And I apply a test step input like this. Fine. Now let us say initially I didn't have this feed forward path. So this is not there, this is not there. So I have two poles in my circuit, and as you know, each pole adds to a delay. So I have two poles, so a lot of delay is there. So when I put it in negative feedback, this will not be really stable, that you guys know already. So now to remedy this, we have introduced this feed forward path. Right? So now let us say I apply this step here at t equal to 0 plus, or just after I apply the step. Do you think this path will respond first or this path will respond first? Yeah, why? Yeah, I mean this also is responding to the same input. So what is?
It is not going to a pole always.
Exactly, as he's saying. So if you look at this path, I have RC, but here I see I am bypassing this section completely, right? So which means the moment you apply any change in your system, it is this path that will respond first. For this reason, we typically call this the fast path. Actually, write it. So this fast path, its job is to provide a quick and a dirty estimate. I am calling it quick because obviously this is the faster path. I am calling the estimate dirty because if I had only the fast path, what can you say about the DC gain of the fast path? GM3 by GL prime, and this gain is obviously much smaller than the gain of your two stage, right? If I just had this, the output accuracy will not be good. But the job of this path is to ensure that the moment any change occurs in the input, it responds immediately and makes sure that the output goes in the correct direction. If the output has to be positive, it makes sure the output rises fast. If the output has to go negative, it makes sure the output goes down fast. And since the output changes quickly, the feedback will be functional nicely. After some time, the slow part starts to take over. So this is the slow part. And here you have sufficient DC gain, which is the product of the gains of the two stages. So this will make sure that the output reaches the final accurate value. So this we will refer to as the slow but accurate part. Is this okay? Again, this is not some extraordinarily new thing. If you are following cricket, you would have noticed it. Let's say in some T20 match, a team has to chase a huge target. Sometimes the team will send some guy in the top order. That guy will not be a batsman. He's a pinch hitter. His job is to just go and score 4s and 6s. In the first 3-4 overs, he scores a lot of 4s and 6s, increases the run rate, he gets out. But by the time he gets out, the run rate is very high. So the proper batsman can come in and nicely make sure the target is reached. Right? And this is something Kolkata Knight Riders used to do with Sunil Narine, right? And how do you think they got this idea? They took this course. Yeah, anyways, but that's what's happening here also. And I mean, even if you recollect, when we looked at the effect of zeros in time domain, let's say I had only a first order system like this. If I apply a step, the output kind of did this. But the moment I added a 0, if you recollect, the output actually showed a sudden jump in the correct direction and went this way. And if the 0 was in the RHP, it would have actually gone down and taken longer. Right? So here I had one pole and one 0. So at t equal to 0 plus, the output will see a sudden jump. But here I have two poles and one 0. So if I apply a step, the output will not see a sudden jump, but it will rise much faster. And in general, I'll leave it for you to work out. You can show that if you have equal number of poles and zeros, if I apply a step at t equal to 0 plus, you will see a sudden jump. You can work out using Laplace domain and all your initial finite value theorems, blah blah blah. But this typically happens. Great. So now let's actually try to understand this more. So let's understand how stable this is and so on. For that, let's look at the pole 0 locations of this. I'll erase all this. Okay, first let's start to find the DC gain. So what do you think is the DC gain here? How can, okay, at least help me find the DC gain. Let's say apply input here. We are looking at the DC gain. What can you say about the capacitors? Open. So if I apply V in here, what can you say about this voltage? GM1 by G1 times V in. This is fine. What is the current pushed out by GM2? This times minus GM2. Fine. What can you say about the current pushed by this fellow? Minus GM3 P in. So we have these two currents. They will flow through which element here? GL prime. So the output is this divided by So I'll just take the magnitude of the gain. Don't have to worry about the negative sign. So if I look at the magnitude of the gain, this is GM1 GM2 by G1 times GL prime plus GM3 by G. Is okay? So how can you approximate this further? I have two terms. Which term do you think will dominate? First term makes sense because it's a product of two DC gains. So I can say that approximately the DC gain is same. It's a product of the DC gains of the two stages. Okay. Cool. So DC gain is set. So now let's look at poles and zeros. So how many poles do you think I have here? 2 poles. This is fine. So what do you think will be the pole locations? Again, remember, if I am finding the pole locations, I can make the input 0. Moment I 0 the input, the GM1 is not functional, GM3 is not functional. You have this fellow and this fellow completely isolated, they are uncoupled. So the pole locations are exactly G1 by C1, and that's it. So do you have 0 in this circuit? We should have, that's what we have been trying to do. Okay. So let's try to find the 0 location. So let me actually go to next page. So I'll erase this. Again, for finding 0, the same old technique we use. Let's assume that the Vout in the Laplace domain is 0. So I'm applying an input here, non-zero input. So then what can you say about this voltage? What can you say about this voltage if this is V in? The current flowing here is GM1 V in, correct? So this current flows through G1 and C1 in parallel. So the voltage is this by G1 plus SC1. Now this times minus GM2 will be the current pushed out. That is one current. So this times minus GM2. Okay. And I have another current due to GM3. How much is that? Minus GM3 V in. So I am looking at this node right now. So I know this, sorry, I have accounted the current from GM2, current from GM3. Sum of these two currents must be equal to 0 because this is 0, so no current flows. Okay, so if you simplify this, what do you get? Okay, let's do it quickly. So GM1, GM2 plus GM3 into G1 plus GM3 SC1 is 0. Right? So S will be minus GM2 M3 G1 right. Just algebra, didn't do anything, can work out. So again here I have two terms in the numerator. Which do you think will dominate? GM1 GM2 or GM times conductance G? Yeah, GM1 times GM2 will be the dominant thing. So again the 0 you can, for practical purposes, you can approximate as, I will not write the negative sign, assume that it is in LHP. So GM1 GM2 by GM3 times C. This is in LHP. Done? So now let's understand how much will be the phase margin in this and how stable this is. And for that, first let's try to plot the Bode plot for this fellow. So I'll again go to next page. So I'll erase this. So let's sketch the Bode plot quickly. Let's assume that this is put in a feedback loop with a feedback factor of beta. So this is omega, this is magnitude of loop gain. This is going to start with some beta A0, right? And I have two poles. So I encounter the first pole, the slope will be minus 20 dB per decade. This is P1. let's say the second pole is also close by. So this goes as minus 40 dB per decade, right? And then what happens? The 0 occurs. So the slope again becomes and what is this frequency? The unity loop gain frequency omega u. So this is just the magnitude. Remember that significant information is present in the phase plot, so never ignore phase. Loop gain, phase of the loop gain omega. So I have 2 poles here. So the phase will start from what value and tend to go to what value? 0 to minus 180. Let's assume the poles are actually at a much lower frequency. The phase actually almost went to minus 180. Okay. I'm not drawing it to scale. Maybe I can do a better job, but it's okay. Let's assume it has gone close to minus 180 already. Then what happens? So then the LHP 0 comes in. What will happen to the phase? It will increase and eventually reach I can do a better job. So now if I look at the phase margin, this is omega u loop. So I see that I have decent phase margin, right? So from this itself you can actually understand. So tell me if I need to have a good phase margin, what can you say about the relative positions of 0 and the unity loop gain frequency? I mean, which should be smaller, which should be larger? The 0 should occur at a much lower frequency. Okay. And again, this is one way in which you can remember the 0 location. See, now at least you know that to get a good phase margin, I have to decrease Z1. To decrease the 0 frequency, I can decrease GM1, decrease GM2, or increase C1. So if I look at my circuit here, if I decrease GM1 or GM2 or increase C1, what can you say about the speed of this path? I am reducing both the transconductors and increasing the capacitance. So the speed will be faster or slower? Slower. So this was already a slow path. If you want to push the 0 to a low frequency, you are essentially making this even slower. Now the 0 you see also depends on GM3. You can decrease the 0 frequency by increasing GM3. If I increase GM3, what can you say about this path? The faster path is becoming faster. So that's one quick way to remember to if you want to push the 0 to a low frequency, you make the slow path slower, fast path faster. So which means to make the slower path slower, GM1, GM2 should come in the numerator because that has to drop. C1 has to come in the denominator because you can increase it to make it slower. And this comes in the denominator. Why is it so?
We are reducing GM1 and GM2.
Yeah, I mean, that's a different aspect, right? Now it's up to you to design. Keeping the GM by GDS same, can you decrease only GM? Same lookup table approach, you keep GM by GDS same, right? Which means GM by ID is going to be constant. If my GM has to reduce, what can you say about ID? Reduce, which means see ID by W should be same. ID is reducing, width has to reduce. As a designer, you can do it. Okay, so this is the Z location, I mean 0 location. So now we are supposed to find the phase margin. For finding phase margin, what is the other information I need? Or for finding phase margin, what is the first thing I should compute? Omega u loop. So let's quickly try to find it. So again, if I write the transfer function here, A of S will be, or let's say loop gain, this beta times A naught. I have a left half plane 0 and 2 left half plane poles. To find the unity loop gain frequency, you substitute S as j omega, take the magnitude, equate it to 1. Again, you will get a long equation. The mathematician in you should feel excited, but the engineer in you should feel sad and ashamed, because that's not what we are here for. So let's see how we can get a better estimate. So tell me from this plot, if let us say the OTA is stable, the omega u loop, do you think is occurring at a frequency greater than these three or smaller than these three? Right? So at least we know this frequency is going to be much greater than all these three fellows. So in that case, how can you approximate the loop gain expression? Beta A naught, I am looking at a value of S which is much greater than S1. So I can say that this is S by Z1. Similarly, this is going to be S by P1 into S by P2. Okay. So I'll continue it here. So you have beta A naught into P1 P2 by Z1 times S. This is still around the unity loop gain frequency. You can approximate this way. So then what is the unity loop gain frequency now? I mean, this should be equal to 1. For what value of S it's equal to 1? Yeah, this value, right? So you can directly write it. Omega u loop is, again, approximately it's beta A naught P1 P2 by Z1. So you can again substitute all the values for A naught P1 P2 and find the final expression. But again, we can do something better. I'll show what you can do better. Let's look at the, yeah, this fellow again. Sorry. So this is the two-stage feed-forward op-amp. Right. Now I know that I am trying to find the omega u loop for this fellow, correct? And I know for a fact that the unity loop gain frequency is occurring beyond the pole locations. So around the unity loop gain frequency, what can you say about the capacitor C1 here? It's like acting like a short circuit. So essentially this is shorted. So then what can you say about the current GM2 is pumping? 0. So which means you can get rid of this. What can you say about GM1? Is it functional? It's nothing connected to the output. So GM2 also can be removed. Right? So now all you have is a simple first order system. For a first order system, what is the unity loop gain frequency? Beta times? Beta? Yeah, I mean, this is the thing. And this is beta, what is A naught here? GM3 by GL prime. What is the pole location? So what is this one? Again, this shouldn't be very surprising because remember that the unity loop gain frequency is a measure of how fast your feedback loop is, right? Higher the omega u loop, the loop can respond faster to any change in the system, right? So we are trying to characterize and find the speed of the system. So the speed of the system, do you think it will be determined by the slower path or the faster path? No. In the sense, I'm not saying, what I'm saying is how fast the system is, right? Depends on how, omega u loop is how fast the system is, correct? That will depend on the fastest path, right? Is that fine? And here, this is the fastest path. Sorry. Yeah, this is the fastest path. So it makes sense that this sets it. What you are saying is a dominant pole. That's a different thing. Correct? Remember that I am looking at how fast the system can respond. The faster path will determine how fast it can respond. So again, you can work out all this. You will still find this to be equal to roughly beta times GM3 by CL. So then let's find out the phase margin. So let's first write the phase of the loop gain. Again, if I assume that omega u loop occurs much later than the two poles, what can you say about the phase added by the two poles? Yeah, minus 180. Again, this is an approximate thing I'm doing. So I've accounted the two poles. What is the phase due to 0? Plus or minus? Plus tan inverse omega u loop by Z1. So then what is the phase margin? Just tan inverse of omega u loop by Z. So once again, you can clearly see if my phase margin has to be higher, the 0 should occur before the unity loop gain frequency. Okay. So this is something you have to do. Great. So now I essentially have two candidates with me, a Miller op amp and a feed-forward compensated op amp. So the natural thing is to see which is better in which scenario, right? So let's quickly do that. First, let me write the results of the feed-forward op amp. So let's say I quickly sketch the feed-forward here. So this is, let us say, GM1. I have the capacitance. I'll just draw the relevant parts. This is GM2. Let us say CL prime, and then I take this, add GM3. Right? Just quick sketch so that you have a feel for what the block is. So here, tell me what is the unity loop gain frequency? Remember, the unity loop gain frequency is the speed, it's a measure of the speed set by the fastest path. Fastest path is your first order system, so that is beta times GM3 by CL prime. Okay. And the 0 location, the way to remember is you try to keep the slower part slower, faster path faster. So this will contain GM1, GM2 in the numerator. And I can also reduce the speed of the slow path by increasing C1. Increase the fastness of the fast path by increasing GM3. See if I can make more space. And we also saw the phase margin is essentially tan inverse of omega u loop by Z1. So which means you can rearrange it. You can find that the 0 is omega u loop by tan of the phase margin. Fine. And here the thing to do to improve the stability is try to keep the 0 smaller than omega u loop. So this is the feed-forward op amp. Now let's look at the Miller compensated op amp. So again, I'll draw a rough block diagram. So this is, let us say, GM1. This is GM2. This is the compensation capacitor. And let's say I also add the 0 cancelling resistor. I'll make this exactly 1 by GM2 so that there is no 0. And then I have CL prime. Just a skeletal sketch I am drawing. Sure. So here, what is omega u loop? What is the omega u loop here? Beta times? You just had your quiz, you should be remembering. GM2 or GM1? GM1? You see? And what is the second pole approximately? Very roughly? GM2 by CL prime. Okay. And here, I don't have 0 here because I have cancelled it. So let's write the phase margin. What is the phase margin here then? The first pole would have contributed 90-degree phase margin. So remaining I have only 90 minus tan inverse of omega u loop by. I don't have the RHP0 because I have cancelled. And the other pole due to this resistor, let's ignore it. Right? Let's assume that's contributing negligible phase. So I will not account it in the expression. Which one? Correct. The resistor introduces other pole, and if you remember, this was 1 by RC times C1 actually. This is C1. Let's assume that this is at a sufficiently large frequency that the phase it adds is very negligible. So here, to keep the system more stable, what can you say about P2 and omega u loop? I'll write it here. P2 and omega u loop. How should these two be related? Second pole should come before omega u loop or after omega u loop? This should be as greater as possible. Again, you can actually rearrange this. If you do this, you should get P2 to be tan of the phase margin times omega u. Just a simple rearranging things using the So let's say now you are in a multiverse, right? So let's say you are in universe 1 where you went and designed a feed-forward op-amp. In a parallel universe, you designed a Miller compensated op-amp for the same specification. So let's say you design for a phase margin of 60 degrees. For 60 degrees phase margin, the 0 should be at what value of omega u loop? By root 3. So here you would have designed the second pole to be where? Root 3 times omega u loop. It's trivial. So now let us say in both the universes your manager goes crazy and wants to make your life difficult. So he or she comes and says that no, my phase margin now is not 60 degree, I want it to be 76 degrees. So let's say in universe 1, what would you do? You want to make this 76 degrees. So 0 should be omega u loop by tan 76. You know what is tan 76? Remember? No? Turns out it is 4. So here for the same thing, I should make P2 to be 4 times omega u. So in universe 2, where you have designed the Miller op-amp, looks like to increase the phase margin, what should you do to the second pole? Increase it. And how can I increase the second pole location? The only leeway I have is to increase GM2. So if I increase GM2, what can you say about the power consumption? That will also naturally tend to increase. We'll make it here. So which means I will say increase GM2, which means increase in the power. Whereas here, if you see, what we have to do to make the phase margin 76 degrees, I have to reduce the 0 location, and this is the 0 location. What is one trivial way to decrease the location of 0? I mean, GM1 and all, you have to change sizes here and there, right? Let's say you have designed it, right? What is one easy change you can do? I can increase C1. And how can I increase C1? You go and put a capacitor there. That's it. You just go and put a large capacitor here. That will increase effective C1. The 0 automatically reduces. Without any kind of overhead, you can actually increase the phase margin. Or as you guys pointed out, you can also reduce GM1 and GM2, which means the power consumption will automatically reduce as well. Right? So this is one advantage with feed-forward op-amps, that you can actually, I would say, get a lower power, or I would say for the same power you can get a higher speed. And phase margin. By higher speed, I mean you can get a larger or higher omega u loop. Okay, it's not here. I will mention. So yeah, that is one nice thing about feed forward. This fine. But of course, it is not as though everything is nice with feed forward. So questions? Okay. So one downside with feed forward is the following. So maybe I have to copy feed forward. Copy this. Yeah. So let's say I take this fellow and put it in negative feedback as usual. Let's say it's unity feedback. And I apply a step here. So let's say the DC gain of this overall op-amp is some A0. So if I were to show it at a simpler block level, this is what I have done. This is the feedforward op amp. I put it in unity feedback and applied a step. The op amp has a gain of A0. So my output will obviously start from 0, and as t tends to infinity, what will be the value to which my output will reach? Here? Yeah, but I mean unit step, let us say. So to what value will it settle to? Huh? Sorry? Okay, I mean I don't know why it's so complicated, right? Let's say it's an op amp with a gain of A. I mean, if you are saying it will settle to 1, will it be exactly 1? I mean, only if the gain is infinity it will settle to exactly 1, right? So with a finite gain A, where will it settle to? A0 by? Fine. The same negative feedback system, A by 1 plus A beta, beta is 1, A by 1 plus A. So it will settle to A0 by. This is what will be the final value. Now remember that this is the feedforward op amp. The moment I apply a step here, which of the two paths will respond first? The faster path will respond first. Okay, so which means because of the faster path, the output will start to rise faster initially. Now if only the fast path was there, what would be the gain of the fast path? DC gain? Gm3 by GL prime. So let's call that gain as some A1. And this is definitely much smaller than A0. If only fast path was active, it would have settled to this value, right? But luckily we don't have the, luckily that's not the scenario because we have the slow path. So maybe after some time, let's say till this fast path is active, maybe I'll draw it, right? This is what will happen if only fast path was there. But now the slow path is there, so let's say after some time here, it will start to kick in and it will try to push the output and eventually it will reach the steady state. Okay. So now from whatever we have seen so far, if I make the phase margin of the system higher, right, what do I do to the zero frequency? I reduce it. If I reduce the zero frequency, what can you say about the speed of the slow path? I mean, the zero frequency if I reduce, what can you comment about the slow path and fast path? Slow path is becoming slower, fast path is becoming faster, right? Fast path becoming faster is nice because initially you will get a quick response. But if the slow path is very slow, this will take forever to go and reach the final value. So this typically will be a problem anytime you have a combination of such fast path and slow path. This is what will happen. Again, without going into a lot of details, I'll just show some simulation results to make the point. So I took two systems in MATLAB. This is a feedforward compensated op amp. So DC gain is 1000, about 60 dB. The unity loop gain frequency is 9.2 megaradians per second. Phase margin is 78 degrees. Now I took another system. It's a two-stage Miller op amp. Again, DC gain is same, about 60 dB. See, omega U loop is same, 9.2 megaradians per second. Phase margin is similar, 75 degrees, maybe slightly smaller. And then I took both the systems, put it in unity feedback and applied a step, and I'm plotting the step response here. Yeah, so the one in blue here is the feedforward op amp, one in yellow is the Miller op amp's response. So this inset is the zoomed in version of the same figure. So as you see initially, the blue curve, that is the feedforward, is actually responding much quicker thanks to the fast path. But if I zoom out and see over a long period of time, looks like the yellow curve, which is the Miller op amp. For the Miller op amp, the output has settled much faster, whereas for the feedforward, it's actually taking much longer. So this is something you might observe if you design for a very large phase margin in feedforward op amp. But in many times you don't care about exact accurate settling. So if you are only interested in high speeds, the general tendency is to use a feedforward op amp. But if you want very, very accurate settling, you probably use Miller. Is this fine? So just one last comparison I'll make and we wrap up. See, you know this op amp is finally going to be used in negative feedback. So let's say this is used in some feedback factor beta. So typically beta is less than 1 or greater than 1. Why? Yeah, I mean, why don't you want a larger part of the output to come to the input? A naught beta should be greater loop gain, right? So I can have larger beta. So why don't I use larger beta in practice? Sorry? What is 1 by beta? The closed loop gain, remember, is approximately 1 by beta, right? And you want a high, I mean, you want some gain in the closed loop system. So typically beta is less than 1. Right? So what is the maximum value of beta then, typically? Okay. So now let us say I have taken a Miller op amp. Okay. I have designed it for a feedback factor of 1. Let's say I get a phase margin of 60 degrees. Let's say the same op amp I use it with a feedback factor of 1 by 2. Can you comment about what will happen to the phase margin? Asked in the quiz also, what happens? Why? Why increases? Omega U loop? Okay, I mean, even without going to algebra, let's say if I look at the Bode plot. So let's say this is how the magnitude looks. This is how the phase looks, right? So let us say right now we have some phase margin. Now if I reduce the feedback factor, what will happen to these two plots? This is, let us say, some beta A naught, right? Now let us say beta is made 1/2. How will the magnitude plot and phase plot change? Magnitude will scale. What will happen to the phase? Phase will be same or will it change? Same. I'm just scaling. It's a scalar factor. It's not adding any phase. So now the omega U loop is here. This is the phase. So phase margin is higher or lower? Higher, right? Because the phase has dropped to a lower value, phase margin is higher. So typically that is one nice thing, that if you have a Miller op amp, if you design it for a worst case feedback factor of 1, you are guaranteed that for any feedback factor smaller than 1, it is even stable, even more stable. Okay. But let's quickly look at the feedforward op amp. So there is a Bode plot here. This is the Bode plot, right? So let's say here I scale the feedback factor. So magnitude plot scales down. So now tell me, this has become more stable or less stable? Earlier I had this much as a phase margin. Now I have only so much, right? So this is not true for a feedforward op amp. If you reduce the feedback factor, it might actually become unstable. So in general, if you want to make a general purpose op amp where you do not know where the op amp is going to be used, could be in a feedback factor of 1, feedback factor of half, or anything. That's why people prefer to use Miller op amps in that case. If you want to make a general purpose op amp and sell it, where you do not know where the consumer is going to use the op amp in, it is much safer to use a Miller op amp, and typically it is compensated for beta equal to 1. Because if it's compensated for beta equal to 1, for any other value of beta smaller than 1, it is guaranteed to be stable. Whereas in feedforward, that's not the case. So if your feedback factor is fixed, you are designing for a fixed circuit, feedforward can be used. Okay, so that's the other difference. Okay. So sorry, I'll stop here.